Have you ever found yourself in a situation where you just really needed a super fast, super accurate 3D scan of something?
Oh, yeah, absolutely.
Maybe you're an architect, needing to model all the little details of an old building, or
Mhm.
perhaps an art restorer trying to document every curve of an artifact.
Or even just getting exact measurements for, like, a custom part.
Exactly.
Mhm.
And we all kind of know how traditional cameras work, right? They snap pictures, frame by frame, capturing everything, whether it's moving or not.
Just constantly recording.
But what if we told you there's this whole new class of cameras, actually inspired by how our own eyes work, that don't really take pictures like that at all?
Mm.
They basically only react to change, and, well, they're starting to revolutionize how we see and measure the world in 3D, especially when speed and accuracy are key. All right, let's unpack this next part because it really does sort of redefine how we see.
It's pretty fascinating stuff.
Today, we're diving into a really interesting new paper, Neuromorphic Fringe Projection Profilometry.
It's a bit of a mouthful, isn't it?
It is. It's by Ashish Rao Mangalore, Chandrasekhar Selamantula, and Chetan Singh Thakur. But it's more than just a long title. It's like a real peek into the future of 3D scanning. It pushes the boundaries using this totally new way of grabbing visual data.
And what's really fascinating here, I think, is that this paper presents a groundbreaking method for 3D reconstruction. It uses these things called neuromorphic cameras.
Right, or event-driven cameras. You hear that term, too.
Exactly. And while, event cameras themselves aren't brand new, this specific work, it really stands out. They're tackling a core measurement challenge, getting precise 3D shapes, but with this completely fresh, event-driven approach.
So they're addressing old problems in a new way.
Precisely. Things like needing incredible speed or handling tricky situations like shadows, stuff traditional methods struggle with. So our mission today is to really understand what these cameras are, how they work, fundamentally, and how these researchers are so cleverly applying them to this established technique, fringe projection profilometry. And crucially, why this new approach isn't just faster, but also way more robust. We'll dig into the how and the why behind it all.
And you might be listening and thinking, okay, fancy cameras, weird fringe patterns. Why should I care?
It's a fair question.
Well, just imagine a world where, say, robots or autonomous cars can see and map their surroundings with just unbelievable speed and accuracy.
It's not just about moving faster, is it? It's about smarter decisions.
Exactly. Like making smarter real-time choices in really complex changing places. Think about a factory floor. A robot using this could instantly see a moved obstacle, replan its path, and just keep going. No pause.
Seamless operation, basically. Safer, too.
Or think about medical imaging. Maybe getting a huge leap forward, giving surgeons real-time, super detailed 3D models during surgery.
That would allow for incredible precision, better outcomes.
Absolutely. So the foundational work we're talking about today has these huge implications. Autonomous vehicles, industrial inspection, even augmented reality making digital stuff blend perfectly with the real world.
It really gets down to how we gather and process visual info at the most basic level, doesn't it?
It does. And this paper offers this radically different way of doing it, potentially unlocking stuff we only dreamed of before. All right, let's peel back the layers on this next bit, because it really is a fundamental shift in how we think about seeing.
It really is.
Forget your standard camera for a second, the kind that takes full pictures, frame after frame, capturing everything whether it changes or not.
Right, the standard snapshot approach.
Neuromorphic cameras are just a whole different animal. Instead of static images, they are event-driven. So for those of us not totally up on the latest sensor tech, what does event-driven actually mean here? It sounds counterintuitive for a camera.
It does, because we're so used to frames. But it's why they're often called vision-inspired imaging devices. They literally draw inspiration from how our own eyes work, specifically the magnocellular pathways in human vision.
Ah, the parts of our visual system good at seeing motion.
Exactly. Those neural circuits in our eyes and brain that are super tuned to detect rapid changes in movement rather than meticulously processing every single static detail all the time. I mean, think about your peripheral vision. You notice stuff moving out there instantly, right? Not necessarily the chair that's just sitting still.
That makes sense.
Neuromorphic cameras try to mimic that biological efficiency. So essentially, each tiny pixel in the sensor acts completely on its own, independently.
So it's not waiting for a signal to capture the whole image at once.
Not at all. There's no global shutter synchronizing everything.
Right.
Instead, each pixel only fires or generates an event when it detects a change in the light hitting it, a change that crosses some preset threshold.
And if nothing changes,
If nothing changes for that pixel, the light level stays perfectly steady, bright or dark. Doesn't matter. The pixel just stays silent. Doesn't send any data, which is, radically different from traditional cameras constantly sending full frames full of maybe redundant information.
okay, can you give us an example, maybe a bit more concrete?
Sure. Let's use a common one. Imagine you're in a pitch black room, right? And there's just one light bulb that flickers on and off, kind of randomly.
Right.
A traditional camera pointing at it would capture, a series of dark frames, then bright frames, dark frames, bright frames. It's constantly recording, generating tons of data, much of it the same. Lots of identical dark frames, lots of identical bright ones.
Right, lots of wasted data.
Exactly. Now, a neuromorphic camera's pixel, looking at that same flickering bulb, it would only record an event precisely when the light turns on, signaling that increase in intensity.
Just at the moment of change.
Just at that moment. And then it would record another event precisely when the light turns off, signaling the decrease. And crucially, in between those moments, absolutely nothing. No redundant data. That's the core of its efficiency.
Wow. Okay, so focusing just on change, not static frames. That obviously creates a very different kind of data stream.
Sure.
What are the big advantages that come out of this for like real-world uses?
That's the key question, right. And the advantages are pretty profound. It's why there's so much excitement around these sensors. The paper highlights several key benefits.
Let's hear them.
First step, sparse data. Because only the changes get recorded, these cameras just slash the amount of data generated compared to frame-based cameras that are always on, always sending full images.
Less data to handle.
Way less. This sparsity is a total game changer. It means you're only processing the meaningful changes, which allows for incredibly efficient data handling and processing. Think about real-time analysis on tiny power-constrained devices like smart sensors, maybe. They just couldn't handle the fire hose of data from traditional cameras.
Right. You only get the actionable info.
Exactly. And that sparsity leads directly to the second big benefit, low latency.
Meaning faster response.
Extremely fast. Events are generated asynchronously, meaning not tied to a clock cycle, and immediately when changes happen. There's no waiting for a frame to finish capturing, no delay tied to a frame rate. They call it asynchronous sensing.
So for things like robots.
Oh, absolutely critical. For robotics, where a millisecond could mean hitting something or not, or for autonomous driving, reacting instantly to a pedestrian stepping out, this low latency is vital.
Okay, sparse data, low latency. What else?
Another really important one, low power consumption.
Because the pixels aren't always on.
Precisely. Since individual pixels are mostly inactive, only triggering when an event occurs, they sip power compared to conventional sensors that are constantly sampling and transmitting everything.
Which means longer battery life for devices or smaller devices.
Exactly. Opens up possibilities for long-running battery-powered sensors or embedding sophisticated vision into places you couldn't before because of power needs.
Makes sense. Any others?
Yes. One more that's truly remarkable. High dynamic range, or HDR.
How does that work here?
These cameras can handle incredible variations in light within the same scene, from really dark shadows to super bright highlights all at once, without the sensor getting saturated or losing detail in the dark areas.
Which is a huge problem for normal cameras, right?
Right.
Trying to expose correctly for both bright skies and dark shadows.
A massive problem. You usually have to compromise. But neuromorphic cameras adapt locally at each pixel. They adjust their sensitivity based on the light they see. This makes them incredibly robust in challenging, high-contrast lighting conditions.
So this isn't just some lab curiosity then. It sounds like it builds on quite a bit of history.
Oh, absolutely. These advantages we're talking about are the result of decades of really pioneering work. It goes way back. You had Mahawald back in, 94, developing the first silicon retina.
Trying to build an electronic eye.
Basically, yeah. And crucially, introducing the concept of address event representation, AER, that's still fundamental today, how these events are packaged with their location and time.
So AER is like the data format.
Exactly. Then you had researchers like Bowen, Color Cielo, and their teams pushing the technology forward, developing better sensors.
And the DVS. That sounds important.
Foundational. The dynamic vision sensor, or DVS, developed by Lichtsteiner and colleagues. That's really the core component that captures these asynchronous events.
Okay, and the paper we're discussing uses a specific camera.
Right, they focus on experiments using the Davis 346 neuromorphic camera. Now, what's interesting about the Davis cameras, including this one, is that they're actually hybrid sensors.
Hybrid, how so?
They have both a DVS, the event-based part, and a standard APS, an active pixel sensor. That's the kind of sensor in your regular digital camera, capturing conventional frames.
So it can do both, events and frames.
Yes, and often an IMU, an inertial measurement unit, for motion data too. But critically, in the Davis, the DVS and APS operate independently. This lets researchers, like in this paper, specifically isolate and study just the event data stream, which is exactly what they did here. They focus purely on the events.
Okay, so let's get down to the pixel level. How does one pixel actually generate an event? What does that little packet of data look like? It's not just a brightness value, you said.
Right, not like a pixel value in a grid. Think of it more like a tiny, precisely timed message. An event gets generated when the log intensity, which is basically the logarithm of the light intensity, it helps handle wide ranges at that specific pixel changes by a certain amount.
Yeah.
A preset threshold,
Yeah.
C.
So big enough change triggers it.
Exactly. And it can be one of two types. An on event, if the intensity is increasing, maybe a light turns on or something bright moves into view.
Okay.
Or it can be an off-F event if the intensity is decreasing, light turns off, or something dark moves across.
And if the light stays the same?
No event. The pixel stays quiet. Saves power, saves bandwidth.
Got it. And the data itself, that little message.
It's structured, very information-rich. It uses that AER format we mentioned, AGT, SexGG, PGG.
Wait, break that down for us.
Sure. T is a super precise timestamp, like down to microseconds. Tells you exactly when the change happened.
Crucial for timing.
Absolutely. Then AGEG are the spatial coordinates. Tells you exactly which pixel fired. The location.
Where it happened.
Right. And finally, PG is the polarity. Tells you whether it was an on event, intensity up, or an off event, intensity down.
So timestamp, location, and direction of change.
Exactly. So instead of a static picture, you get this continuous, asynchronous stream of these tiny info-packed messages from all the active pixels. Over time, this forms the event stream. Figure 1 in the paper shows this really well, how a moving stripe pattern triggers these on and off-F events across different pixels as it sweeps by. It's a very dynamic way to capture info.
Okay, so these cameras sound amazing for seeing motion, for seeing change really fast and efficiently. But how do you go from just detecting those fleeting changes to building a full, solid 3D model of an object, something static? That feels like a big jump.
It is a big jump. You've put your finger on a really key challenge. It's a hard problem. While these cameras are fantastic for things like optical flow tracking movement or finding moving features.
Things that inherently involve change.
Exactly. Generating a dense 3D reconstruction, like a full surface map, using only the raw event data is inherently tricky because events are about change, right? Not static form. If an object is perfectly still and the lighting's perfectly steady, the camera might see almost nothing.
Even though the object is right there in 3D.
Right. It's like trying to describe a statue just by noticing when the sun casts a shadow on it differently. You get some information, but maybe not the whole shape.
So if events alone are tough for static 3D, how have researchers tackled this? How do they use these cameras' strengths to build those 3D models? They must have some tricks up their sleeve.
They absolutely do. It requires some creative thinking. And the paper points out that often the solution involves using neuromorphic cameras in conjunction with other sensors or using specialized techniques.
Combining them with other tech.
Right. One really effective approach has been IMU integration, using an inertial measurement unit.
The motion sensor.
Exactly. So researchers like Rebek and his team combined a DVS with an IMU. The DVS sees the visual changes. The IMU tells you how the camera itself is moving, rotating, accelerating. By fusing this data, they could do sparse 3D reconstruction, basically figuring out where edges were in 3D space by correlating visual events with camera motion.
So using the camera's own movement to help map things out.
Precisely. And then Kim and colleagues took it even further. They also used a DVS and IMU combo and achieved dense, real-time 3D reconstruction. Plus, they could estimate the full 6 degrees of freedom, motion, position, and orientation.
Wow, real-time 3D mapping.
Yeah, and they even showed it could do simultaneous localization and mapping SLAM more efficiently than frame-based cameras.
SLAM is what robots use to navigate unknown spaces, right?
Exactly. Building a map while figuring out where they are in that map, doing it faster and more efficiently with event cameras is a huge deal for robotics. It means robots that can understand and react to their surroundings much quicker.
Okay, so I am user one way. What else?
The other major strategy, and this leads us straight to our paper, is using structured light projection.
Structured light, like projecting patterns.
Exactly. You project a known specific pattern of light onto the object, and then you look at how that pattern gets distorted by the object's shape.
Ah, I've seen systems like that.
Right. Researchers like Brandley use this, projecting simple lines onto terrain to map it out. Matsuda and his team came up with something called motion contrast 3D scanning, or MC3D. They cleverly adapted traditional line scanning to work with event data, making the scanning itself trigger the events.
So making the light provide the change the camera needs.
Precisely. And LaRue and others also showed that using structured light patterns with event cameras was definitely feasible for getting depth.
So this idea of structured light, deliberately projecting a known pattern, that seems like the key. The bridge connecting these event cameras, which see change, to the problem of measuring static 3D shapes.
That's absolutely it. Structured light is the crucial bridge here. It's the core idea that lets Mangalore, Silamantula, and Thakur create their neuromorphic fringe projection profilometry. By projecting a dynamic structured light pattern, they engineer the change the camera needs. They essentially make the light itself move, triggering the events and unlocking the camera's speed and efficiency for precise 3D measurement. It elegantly solves the static object problem.
Okay, fringe projection profilometry. Fringe still sounds a bit out there. What exactly is it and how does it normally work, the traditional way?
Yeah, the name sounds fancier than the concept, maybe. In optics, a fringe just means a 2D sinusoidal pattern. Think of like smooth, wavy stripes of light and dark.
Like ripples on water, but made of light.
Exactly like that. So traditional FPP uses a standard projector to cast these static wavy patterns onto an object. And then a normal frame-based camera takes pictures of how those patterns look on the object's surface.
And the shape distorts the pattern.
Precisely. The way the stripes bend, stretch, and shift tells you about the object's 3D shape. By analyzing those distortions, algorithms can calculate the depth and build a really accurate 3D model. It's a well-established, reliable technique.
Okay, but hang on. If neuromorphic cameras only see change, and traditional FPP uses static fringes, I see a problem. What happens? Does the camera just see nothing?
You've nailed the fundamental conflict. That's exactly the issue. The researchers state it very clearly. Conventional FPP systems use a static fringe pattern, which is not suitable, since a neuromorphic vision sensor would not record any events for static stimuli.
So no change, no events.
No events, no data. It would be like pointing the camera at a painted wall. Nothing's changing, so the camera stays silent. It's a complete roadblock for using neuromorphic cameras with standard FPP.
Right. So static fringes are out. How did Mangalore, Silamantula, and Thakur crack this? What's their clever workaround?
Their solution is actually quite elegant, really. Instead of a static pattern, they use a moving fringe pattern that propagates laterally over the object being scanned.
So the stripy pattern itself is moving, sweeping across the object.
Exactly. Picture those wavy stripes continuously shifting sideways, like waves washing over the object.
Ah, and that creates the change the camera needs.
Precisely. This constant movement means that as the light and dark bands of the fringe sweep past any given point on the object, the light intensity at the corresponding camera pixel is constantly changing, going up, going down.
Triggering those on and off events.
Triggering the events continuously. It's like, a barcode scanner. The barcode itself is static, but the laser moves across it, creating the changing signal. Here, the pattern itself moves, generating the signal across the whole object. It turns the static measurement problem into a dynamic perception problem, perfectly suited for the camera.
That is a really smart way around it. Just make the stimulus dynamic. Yeah. But does this moving fringe offer any other benefits? Besides just making it compatible, does it improve things?
Oh, definitely. It's not just a workaround. It unlocks some key advantages inherent to the neuromorphic approach. The paper highlights two big ones.
Okay, what are they?
First, faster scanning. Because the whole pattern is moving and generating events everywhere simultaneously, they say it's equivalent to performing several line scans all at once.
Instead of scanning one line at a time like some older system.
Exactly. Traditional line scanning can be slow because you have to mechanically move the line across the object. Here, the entire pattern provides data in parallel, so it's inherently faster than a single line scanning method. The total scan time is much shorter.
Which is great for speed. What's the second advantage?
This one's a big deal, especially for real-world use. Efficient shadow handling.
Ah, shadows.
I
Always a
know.
problem in optical scanning, right?
Always. In traditional FPP, shadows create dark areas that look just like the dark parts of the fringe pattern. It confuses the algorithms and leads to errors in depth. You often need complex software fixes or multiple scan angles.
So how does the neuromorphic approach help?
It simplifies things dramatically. Remember, neuromorphic pixels only fire when there's a change in light. If a pixel is looking at a shadow cast on the object,
The moving fringe pattern isn't visible there.
right, so there's no changing light intensity, the pixel stays silent, it generates no events. Shadows become simply regions in a scene that do not trigger any events.
So they're just areas of inactivity.
Exactly, areas of no data, and that makes them much easier to detect and then deal with. The paper explicitly says detecting shadows and eliminating their adverse influence is much easier in neuromorphic FPP. It turns a major source of error into a relatively simple problem of identifying areas with no signal. That's a huge boost in robustness.
Okay, that shadow handling is brilliant. Let's get into the real mechanics now. How does the measurement actually happen? The paper talks about a projector camera arrangement. What does that physically look like, and what's the exact pattern they're projecting?
Right, let's visualize the setup. Figure 2 in the paper shows it clearly. It's a classic stereo configuration. You've got the Davis 346 camera and the projector sitting side by side, separated by a known distance that's the baseline, B.
Like our two eyes are separated.
Exactly the same principle needed for depth perception. And the projector isn't just shining random light, it's emitting that very specific propagating fringe sinusoidal pattern. Mathematically, they describe it as SXYT equals A cos equi plus dot T.
Okay, let's unpack that equation a bit without getting lost in the math.
Definitely. So A is just the amplitude, the brightness. The cos part tells you it's that wavy sinusoidal shape. Equi means it's oriented horizontally. The stripes run side to side, and UC is the vertical spatial frequency. That just means how close together the stripes are vertically.
How dense the pattern is.
Right. And the crucial part is plus poten. The tent represents time, and ton is the temporal frequency. This is what makes the pattern move. It dictates how fast the whole pattern shifts sideways over time.
So it's a horizontally striped pattern continuously sweeping across the object.
Precisely. And again, figure 1 is key here. It shows how this moving wave causes those on-amen and off events at different pixels as the bright and dark bands pass over them, each event tagged with its time and location.
Okay, so we've got this stream of precisely timed on-in and off events pouring in from the camera. How do we actually convert that raw data into something meaningful, like a 3D shape? How do we get depth out of these fleeting changes?
This is where the magic of phase estimation comes in. It's the absolute core of the measurement process. Because the projected fringe pattern is periodic, it's a repeating wave, the stream of events generated at each pixel also becomes periodic over time.
The events arrive in a repeating pattern.
Yes, matching the frequency of the moving fringe. The key insight is that the phase of this periodic event stream, basically, where you are within that repeating cycle at any given moment, directly encodes the depth information.
How do they get that phase?
They compared the timing of event streams from different pixels. Specifically, they calculate something called the cross-correlation between the event stream from a pixel looking at the object and the event stream from a known reference pixel, maybe on the background.
Cross-correlation.
Yeah.
That measures similarity between signals, right?
Exactly. It finds the time lag or delay, let's call it Tmax, XY, at which the two event streams align best. This time lag tells you how much the pattern's arrival was shifted or delayed by the object's height at that point compared to the rep.
So the time difference reveals the depth effect.
Precisely. And from this time lag Tmax, they calculate the wrapped phase using the formula XY0. So the measured time shift Tmax multiplied by the known temporal frequency WAV of the moving fringe gives you the phase.
But why wrapped phase?
Because the pattern is periodic, the phase repeats every cycle, like angles on a circle going from 0 to 360 degrees or 0 to 2 radians. So the raw phase value is wrapped within this range. It tells you the position within one cycle, but not necessarily which cycle.
Got it. So phase holds the depth info. What about those shadows again? How does this phase calculation deal with the shadow regions where there are no events?
This is where that clever shadow handling really integrates with the measurement. As we establish, shadows do not activate pixels. So in those regions, there's no event stream to calculate a cross-correlation from. The phase would be indeterminate, essentially garbage data.
Leading to holes or errors in the 3D model.
Right. So their smart fix is phase in painting. First, they detect these shadow regions simply by seeing where there's no activity, no events being generated. The camera tells them directly.
Okay.
Then they inpaint the phase in those shadow regions. They fill in the missing phase values by borrowing the corresponding values from a reference phase map.
And where does this reference map come from?
It's generated during a one-time calibration step before scanning the object. They project the exact same moving fringe pattern onto the flat background reference plane without the object present. This captures the ideal phase values everywhere.
Like a baseline measurement.
Exactly. So when the object casts a shadow later, they can look up the correct phase value from this pre-recorded reference map and patch it into the shadowed area of the object's phase map. It's like using a perfect template to fill in the blanks.
That's really clever. Does it work well?
Extremely well. Figure 3 in the paper shows it beautifully. You see the raw unwrapped phase, figure 3B, with big errors due to shadows. Then you see the in-painted wrapped phase, figure 3C. And finally, the corrected unwrapped phase looks so much cleaner and more accurate. It visually demonstrates how this step massively improves the result.
Okay, so we got the wrapped phase and we fixed the shadows with in-painting. But you said wrapped implies it repeats. How do they get continuous depth? And then the actual measurements?
Correct. Unwrapping is the next critical step. That wrapped phase, Y, repeats every 2 radians. To get a smooth, continuous depth map, you need to unwrap it, figure out how many full 2 cycles need to be added or subtracted at each pixel to remove those jumps.
How do they do that reliably? Phase unwrapping can be tricky.
It can be, especially with noise. They use a sophisticated algorithm that's designed to be robust. It doesn't just go pixel by pixel. It follows paths based on a reliability score, basically trusting the phase data more in some areas than others, which helps it handle noise and discontinuities better.
Okay, so now we have a continuous unwrapped phase map for the object. Let's call it phi-xy. What's next?
You also need the unwrapped phase map from that initial calibration scan of the reference plane at phi-xy. With both of these unwrapped phase maps, you can finally calculate the actual depth map z's xy.
The real-world distances.
Exactly. This is done using the standard geometric triangulation principle. The formula essentially looks at the difference between the object's unwrapped phase and the reference plane's unwrapped phase. This difference tells you how much the object deviates from the background.
And relates that phase difference to depth.
Yes, using the known geometry, the spatial frequency of the fringe, the baseline distance between the camera and projector B, and the distance from the camera to the reference plane. Plugging these known values in with the measured phase difference allows you to calculate the precise depth Z for every pixel using triangulation. It's the final step that turns those light patterns and time shifts into physical dimensions.
That's quite a journey from events to phase to depth. So, practically speaking, how do they actually create that vital moving fringe pattern in their lab? Do they need some complex custom projector?
Surprisingly, no. It was actually quite straightforward, leveraging standard software tools. They used OpenCV, the open source computer vision library.
Oh, okay. Very common.
Right. First, they generated a static fringe pattern image. They set it to have 10 cycles in one frame, meaning 10 full light-dark waves vertically within the image height. The camera resolution, 346 by 260 pixels, dictated the practical limits here.
So they made a still image of the pattern first. How do they make it move?
This was the really clever, simple part. They generated a video by rolling it over in a circular fashion with 1 row shift downward per frame.
Rolling it, like shifting the image down 1 pixel line each frame.
Exact. Imagine taking the bottom row of pixels and moving it to the top and shifting everything else down 1 row. Do that for each frame of a video, and the pattern appears to smoothly scroll or propagate downwards.
Creating apparent motion from a static image. Neat trick.
Very neat. They generated this video at 20 frames per second, which meant the pattern effectively scanned downwards at 20 rows per second, a really practical way to get the dynamic stimulus they needed without fancy hardware.
Okay, so that's the pattern generation. What about the actual physical setup in the lab? What hardware did they use?
The experimental setup, shown back in Figure 2, was pretty standard for this kind of research, but carefully assembled. The key components were the Davis 346 camera, our event camera, and a Texas Instruments DLP Lightcrafter 4500 projector.
DLP projector, okay.
Right, a common high-resolution digital projector. These were mounted in that stereo setup, side by side, separated by that known baseline distance B, which is crucial for the final depth calculation.
And they mentioned calibration was key.
Absolutely essential. Before scanning any object, they did that critical calibration step, projecting the moving fringe pattern just onto the reference plane without the object. This captured that all-important reference phase map needed for the calculations and the shadow in painting.
Got it. Calibrate first.
Then they'd place the object, like the swan figurine in the setup, project the moving fringe onto it using the projector in video mode, and record the data from the Davis 346. And importantly, they specifically state they recorded only the all-N events for their reconstruction, really focusing on proving the sufficiency of event data alone.
Even though the camera could provide OAF events and frames, too.
Right. They wanted to isolate the contribution of just the on-N events for this proof of concept.
Managing all this data, especially the precisely timed event data, sounds like it needs specialized software. What did they use?
It definitely does. You need software that can handle these high-speed asynchronous data streams. They use the RPGDV SROS package.
Okay, sounds specific.
It is. It's built on another library called libcare, and both are well-known in the neuromorphic research community. The key thing is that RPGDV SROS integrates with ROS, the robot operating system.
ROS, right? Widely used in robotics.
Exactly. And using ROS was a big help because it provides readily available camera calibration packages. Since the DVS event sensor and the APS frame sensor in the Davis 346 share the same lens, they could actually adapt these standard ROS calibration tools, typically used for frame cameras, to accurately calibrate their whole setup, the DVS included. It streamlined things a lot.
Okay, they've got the setup, the software, the theory. The big question: did it actually work? What kind of results did they get? What did they manage to scan?
The results are really impressive, honestly. They provide very clear visual evidence that the method works well. They tested it on a few objects, including a fairly detailed figurine of a swan, and even the right hand of the first author.
So complex shapes, organic shapes.
Yes, showing it's not just for simple blocks. And again, that shadow in painting really shines in the results. Figure 3 makes it so clear you see how it corrects those erroneous estimates caused by shadows, leading to a much cleaner, more accurate, unwrapped phase map.
It really fixes the shadow problem visually.
It does. They also mentioned that even though there's always some noise in raw event data, their phase unwrapping algorithm proved quite robust, handling it well, and producing coherent results.
So they got the depth maps. What then?
After getting the depth map ZXY, they did a little bit of standard post-filtering, specifically using a 5x5 median filter that just helps smooth out any random noisy pixels or outliers. And they did background removal using a simple threshold to isolate the object.
Standard cleanup steps.
Pretty standard. And then Figure 4 shows the whole pipeline visually. It goes from the raw event data, which isn't explicitly shown but implied, to the calculated depth maps. Figs 4A 4-pin, which look like grayscale images where brightness equals depth.
Okay.
Then from the depth maps, they generate 3D point clouds. Figs 4B4, that's just a collection of 3D points floating in space representing the object's surface.
The raw 3D coordinates.
Exactly. And finally, they connect those points to create beautiful 3D meshes, Figs 4C4. These are the fully reconstructed surface models of the swan and the hand, really tangible, detailed 3D results.
Derived entirely from those on-end events.
Entirely from the ante events. And that's their big conclusion. The experiment demonstrates that using only the event data suffices to perform reliable 3D scanning. It's a powerful validation. And super helpfully, they even made their Python code for getting the point cloud from the events publicly available.
That's great for the community. It lets others build on it.
Absolutely. Fosters further research and development. #tag us #outro.
So wrapping this all up, what's the big picture here? What we've really seen today is a genuinely novel way to do 3D reconstruction, isn't it?
It really is.
This neuromorphic FPP system, it kind of sidesteps the old limitations of frame-based cameras by fully embracing the way these event sensors work. It's not just an improvement, it feels like a different philosophy of seeing.
I think that's a great way to put it. And the key takeaways are pretty clear and impactful. First, it's demonstrably faster than things like single-line scanning because it's capturing data across the whole object at once. The speed is really just limited by how fast the camera can output events.
Speed is a big one.
Definitely. Second, and maybe even more important for practical use, it's significantly more robust against shadows. What used to be a major headache becomes a simple matter of detecting no activity.
Turning a weakness into something manageable.
Exactly. And third, maybe the most fundamental point, they showed that only the event data suffices for reliable 3D scanning. It validates this whole event-driven approach for precise measurement.
That's hugely significant. Now, they do acknowledge a current limitation, right? The resolution.
Yes, they mentioned that the resolution of the 3D reconstruction is limited by the resolution of the neuromorphic sensor array itself. And currently, event sensors often have lower pixel counts than high-end traditional cameras.
So the 3D models might not be quite as detailed yet.
Potentially, yes. But, and this is crucial, the paper ends on a really optimistic note about this.
How so?
Well, if we connect this to the bigger picture, they point out the rapid advances taking place in neuromorphic sensor development. New sensors with higher resolutions are coming out all the time, just like traditional camera sensors got better and better over decades. The same is happening, perhaps even faster, with event sensors.
So that resolution gap is likely temporary.
Very likely. This deep dive, it's not just about a cool new way to scan a swan figurine. It's really a glimpse into a future where our machines perceive reality differently, more efficiently, more robustly.
So thinking about that future, it does raise a pretty big question, doesn't it? How might our world actually change when the cameras in our devices, our robots, our cars, when they stop being like passive video recorders just capturing everything?
And become more like biological eyes, reacting instantly with minimal power only to what's actually changing, what actually matters.
Exactly. What kinds of applications, things we can barely imagine now, suddenly become possible when machine perception is defined by change, not just by static frames?
It opens up so many possibilities. Ultra-low power sensors that monitor constantly but only wake up when needed. Robots that are truly agile and adaptive in complex, unpredictable human environments. AI systems that have a much more dynamic and perhaps intuitive understanding of the world around them.
The implications feel enormous, from smarter homes to truly perceptive AI.
It really could be transformative.
It's a fantastic thought to end on. What happens when seeing fundamentally changes for our machines?
Yeah.
Definitely something to ponder. Thank you so much for walking us through this fascinating deep dive today.
My pleasure. It's truly exciting work.